Now we will discuss inferential statistics. And in order to do that, I ask you to take a look at the paper that I sent you. It was a bit complex because it was using a statistical model called structural equation modeling, which is a bit more complex than usual, but I ask you to focus on the correlations. So basically today we will be mainly discussing correlation, which is a really, really simple statistical model. However, I want you to understand the main concepts in inferential statistics, and this is what today is about. But before starting, I would like to ask you, what do you think when you hear of a p-value? What a p-value means to you? What kind of interpretation are you doing of p-values when you come with the concept when you are reading papers from psychology? Are you familiarized with p-values, with the concept? Have you heard of it?
It's how likely your data would have resulted or occurred under the null hypothesis.
Okay, so it is a way of a confirmation, right, of your hypothesis. You are using it as a way because you are testing the null hypothesis. The null hypothesis is always there is no effect, right?
Yes.
So if you reject the null hypothesis, it means that you have an effect. This is why we like it, right? We like a p-value that is really, really low, lower than 0.05, because we think it is unlikely to have a value as extreme as the one we are getting from our sample if there is no effect, right? So, okay, we will discuss a little bit more about p-values because I already mentioned it. It can be misused. We can interpret the p-value in a wrongful way, and more importantly, not just because you have a p-value that is below the alpha level of 0.05, this means that your hypothesis is strong or that you can help your hypothesis. It doesn't mean that.
Or could I say that the lower the p-value, the more likely it is that my result is more than just statistical noise?
Yes, this is what we will discuss today, and the key part is that the p-value, Godehard, it's a test that will help you find out the probability of a value as extreme as the one you are obtaining if the null hypothesis is true. So the thing here is that the p-value is just an argument to reject the null hypothesis, but not to accept it. So I fail to reject it, but I don't accept that I have an effect. And this is the main thing that a lot of people is taking like granted. It is my p-value is so low that I must have an effect. And this is not the case. And this is the main misuse. So p-values should always be interpreted with other values that we will discuss today. So this is the important part that you must take away from this lesson. So the p-value is important because we are testing the null hypothesis. The null hypothesis is directly related with our research question. And we have different statistical models to test this null hypothesis. And we will discuss this today. However, not just because we have a statistically significant value, this means something good for our research. And we will see this with the example of the paper that you already take a look for this class. So we will be practicing with this paper, and I'm glad to hear that you are familiarized with p-values, and I think it will be very clear for you like what kind of things p-values can help you with and what kind of things you cannot conclude with a p-value that is really, really low. And the main thing is that you cannot conclude that you will accept your hypothesis. This is not what a p-value should tell you, and that you have an effect on your variables. So p-values also won't tell you this. And this is the main thing you must know now on, okay? Okay, so let's start. Let me share some slides. Okay, here, let's see.
So what is the best definition of the null hypothesis? Is it like the claim that the effect that is being studied does not exist? It's a non-existence claim. So we are studying a certain effect, and the null hypothesis says the effect that we are studying in reality does not exist. Is that?
Your null hypothesis is that you have no effect. If you have a p-value that is really, really low, then you fail to reject the null. This means that it is very unlikely that you have these results if there is no effect in reality. So you are.
But you're studying an effect. You assume that there is an effect, and then the null hypothesis says, well, you assume it, but in reality, it's not there.
Yeah, well, the statistical test must assume there is no effect. This is the starting point. And you have to find evidence, Godehard, that you have an effect. So the p-value being really low is one clue for you to tell you that you may have an effect, but you must look for different clues in order to conclude that you have the effect. Exactly. So we will go through specific concepts about the null hypothesis, and I will show you some examples of null hypothesis. We will discuss this, and at the end we will go to the paper and we will try to look at the p-values there and at the conclusions of the authors, and we will take a look at that. Okay. So let me try again to share. Okay, let me share this here. Multiple screens. I'm having an issue with multiple screens here in my setting, and this is why I cannot select the right one. But I think you are looking at right now. Can you tell me if you see the presentations?
Yes, we're looking at your presentation.
I think so, right? Yeah.
We're looking at module 3 introduction.
No, Godehard, I am unable to hear you.
We're looking at module 3 introduction to inferential statistics.
Okay, something is not going well with my audio, so let me change it again. Let me change my setting. I think I know what is the problem. Let's see. Can you try now to say something?
Hello? Can you hear me now?
No, I still cannot hear you.
Can the others hear me?
Yes, of course. We can hear you, Godehard, and we hear you, Gina. Clear and brightening? No, I don't know.
Maybe you have set the window that you've opened so that takes over the sound. That's a possibility.
Yeah, something is off with the setting that I have with my computer. So I will try closing the meeting to see if I can connect with the proper audio and video. So please connect again. Yeah, I'm sorry about this.
Okay, no problem.
In the previous session that you had with me, we were discussing descriptive statistics. So we use descriptive statistics in order to make sense of quantitative data by using graphs in order to find out the distribution of our sample, right? So we can use the graph to see the distribution, or we can summarize values. For example, obtaining the mean, obtaining the variance or the standard deviation in order to see how our sample distribution is actually showing us the shape, the proper shape, and we also discuss the normality of the distribution and the importance of the normality of the distribution. So all of this data, the mean, the standard deviation, the variance that we can calculate with descriptive statistics are actually the basis of the inferential statistics that we will apply. So inferential statistics are using the limited information that we have from our sample as the basis for reaching general conclusions about the population from which the samples were obtained. So in this case, in inferential statistics, I want to make predictions. I want to make estimations or generalization to the broader population, while in descriptive statistic, I was just talking about the sample that I got. So this is why inferential statistics is widely used, because it's more sexy, because you can take one sample and then trying to make inferences, estimations, predictions about finding the same phenomena in a broader population, right? So this is how we use inferential statistics. And this is why they are important. It is all about making predictions. So how do we make predictions in social sciences and in the humanities? As I already told you, first, we must start with a research question. And now, for example, let's have this research question. What if I'm asking, do religious individuals exhibit greater personal growth after experiencing adversity in comparison with non-religious individuals? This is, for example, one research question that I can try to tackle. And then I can measure, right? I can measure like a group of religious individuals and a group of non-religious individuals, and then I can apply a scale. Like, for example, if I want to test how resilient they are, I can use the RSA, for example, to test them. And then when I have my sample, and then when I have my data, then I can calculate the mean, as we already saw. Remember, the mean is just the average of the scores, right? So on average, most people, like, what are they scoring? This is the mean. And then we calculate the standard deviation. As we already saw, the standard deviation is calculated with the variance of the data. So the variance is like one thing is to know what is the mean, the average of the value, and another thing is how much these values vary. For example, if I find a lot of individuals scoring really high and really a small amount of individuals scoring really low, then I have like really big variance in my sample. And then this sample won't have a normal distribution, because you know the normal distribution will have around 60%, 68% of all the data within one standard deviation. So calculating the standard deviation is about how much the data is varying. So if I have this, all of this is descriptive statistics. So I have my mean, I have my standard deviation, I have the size of my sample. I tested 100 individuals. So here I can find that the religious individual, they score 128 points in this scale. And the non-religious individual, they score 115, right? So I have some results. This is all descriptive statistic. But now the question is this difference of 30 points in each scale, just 30 points above matters? Does it mean something? Right? This is a question that we want to answer, because one thing is to have the absolute value of the mean, and another thing is to know if this amount of excess of the religious individual versus the non-religious individual actually matters statistically or should be taken into account. So if I want to answer if this difference matters, then I care about the magnitude of the phenomena that we are observing. And for that, I use the effect sizes and the confidence interval in order to know how strong is the effect, how big is the change in more resilience in religious individuals versus non-religious. So for that, I apply my statistical test, and then I look into the effect size to see how strong it is, to see how much it matters that the religious individuals are scoring higher than the non-religious individual. So this is one question. But the other question we can ask is, are the results that we are observing in our sample due just to random variation? Is just like for luck? Or even are they due to sampling error? Maybe I was doing something wrong when I was testing them, and this is why I'm finding this difference between these individuals. Okay, so inferential statistics will help you to answer both questions. Like, how much is the difference between these two scores? Do they matter? And really, these results that I'm getting, are they due to simple random variation or sampling error? Or is it because we actually have an effect of this in the population? So this is the role of inferential statistics, like provide information about these two very important questions. And for that, like answering the second question, it is due to random variation, it is due to sampling error. For that, I will require to look into the p-values, just for that. So the p-value will tell me how likely it is to obtain a value as extreme as this if the null hypothesis is true, right? So for this is the p-value, but for knowing how strong is the effect, I need to calculate parameter estimates. This is the important part. So you need to take care of both in order to be able to predict properly using statistical analysis, and in order to answer your research questions that you are using quantitative data for. So this is how we use inferential statistics. So we want to make predictions. We want to bridge the gap between the limited information that we have from the sample and to the entire populations. So inferential statistics use models that represent the processes of how the world or the mind works. So we use statistical models in order to predict, right? In order to predict how the world is or how individuals behave or will behave. So this is why we are always talking about fitting your model, because technically, let me put it in a different way. We are using the same information from descriptive statistics. We are using the mean, the standard deviation, the variance. We are using the same data, but we are plugging this data into statistical models that are represented in a mathematical way. So the model will test specific relationships of these values in order to be able to predict. So this is how it works. So we start with the research question, then we go sampling, obtain our data, we select the model, the statistical model we want to use or we have to use, Then we feed our model to our data. This is why we say feeding your model. This is why we say overfeeding your model, right? And then we can reach to conclusions. So for you to have a better idea of these models, so we have different statistical models. Some of the more popular, I have it here. We have linear regression, we have t-tests, we have ANOVAs, we have structural equation modeling, but we have many more. We have factor analysis, we have MANOVAs, we have ANCOVAs, we have time series analysis. Like, we have many kinds of statistical models. And obviously, I won't overwhelm you telling you about all of them. So the important thing that you have to know is like the names of the most important ones that you have here, and we will discuss briefly the difference between these models. But the main thing that you have to take away is that each one of these models and all of the models, they will give you parameter estimates as an output and a p-value, all of them. You need all of them because remember, these two will answer your question about, is it a big effect that I have, or is it a significant effect, right? So all of the models will give you this output. So you have to keep this in mind. Okay, so statistical models are really, really important. Like, we can use in many different disciplines a model in order to make predictions about future events, about understanding how the world works, or conducting simulation. We can also do this. This is why having these models will help us to bridge between abstract concepts or ideas and the reality that we are finding in our sample. So this is why we are talking about statistical models today, and statistical models are just a mathematical representation or a framework used to describe and analyze relationships between variables, right? So I have here for you some examples of how we can represent statistical models. So, for example, it can be really simple or it can be really complex. For example, before we were talking about religiousness, and we were wondering if being religious will lead you to be more resilient after an adverse event, for example. And I can represent the model visually in this way. I can have this square, and I can have this arrow with one direction, right? And I can have the other variable here. When I am talking about inferential statistic, I have an outcome variable and I have a predictor variable, okay? So this is a statistical model, and this model specifically, it is discussing cause and effect relationship. This model, because the arrow is in this direction, it is saying that religiousness will influence resilience and not the other way around, because the arrow doesn't go two ways. So I can represent the statistical model in this way, and I can actually test it. I can actually test it if I do it graphically, and I can use, for example, Amos. Amos is a software that I can input these graphics, and then it will test the strength of the relationship in this cause and effect model. So in this case, the statistical model that I have to use is linear regression, because I am talking about cause and effect. However, if I want to talk about relationship going in two directions, I mean that it can be possible that the religiousness will influence the levels of resilience, but also the other way. Also, maybe being resilient will lead you to be more religious. So this is a different model. This is a correlational model, right? So I have to use a correlation in order to test this model. These are just a representation. This is a representation of a statistical model. I have another one here, for example. Here you have two arrows. This means a correlation because psychotherapy may influence the level of anxiety, like how many therapies are you having? It can influence the level of anxiety you are feeling. However, it can also be the other way around. It can be that because you are anxious, you are going more to therapy, right? So it can be two ways. So this is a correlational model too. Now, this is the graphical representation of the model, of a correlational model. However, here you have the mathematical representation of the model. So here is just, you have the covariance of the variable religiousness and then the variable resilience divided by the standard deviation of both variables. This is the statistical representation of the same model, this model. So if you input this in Excel, you will have a result which is an R, because the correlational model is using Pearson R. You will have the R, or if you input this in Amos, for example, you will have the same result. You will have the R and you will have your p-value. So by feeding a model to the data, we can actually test and make predictions and quantify the strength and the direction that we have between the variables, okay? So this is how we represent statistical models. However, this one, which is the correlational model, is really simple. Like, is there a correlation between religiousness and resilience? Do they move together? Like if one goes up, the other goes up or down in a linear relationship? Or we can have a more complex model, right? In this kind of model, like I have different variables, and different variables are connected to each other in different ways with different relationships. So this model is more complex, and like a simple model like correlation or like linear regression won't be enough in order to test these many variables and these kind of connections between the variables. So for that, we use a structural equation modeling. This is why this is a more complex model. And this model was the one that the paper that you review for this class was testing. They were testing this model, but they were actually making a modification to the model. So they didn't use all the variables, and they make some changes regarding the directions. So this is how we have statistical models being more complex. So this is tested with the structural equation modeling. They use structural equation modeling in order to test it. As you already reviewed the paper, they concluded that the original model works. So this can be debatable regarding the results they are getting, because here, for example, let's explore this model. Here I have an arrow. This arrow is just going in one direction. So this means I have a predictor variable and an outcome variable, right? I don't have a correlation here. And I have a strength of the relationship. So the strength here is 0.23. Now, I would like to ask you, do you remember if 0.23 of a strength is a strong relationship? Do you remember this? The relationship between variables, when I have a perfect relationship, I should have a 1. A perfect relationship is of 1. So a 0.99 relationship is super strong. And if I have a 0.10 relationship, is really, really low, okay? So maybe you remember a little bit more of this now. This kind of thing, you have to understand it. And today, I would like you to really tackle this concept regarding the strength of the relationship. So if you have a positive relationship, a strong positive relationship, we are talking about 0.90, for example, to be really strong. If I'm talking about a negative relationship, then I am talking about minus 0.90, right? And what does it mean, a negative relationship? It means that if one variable goes up, the other one goes down, okay? This is a negative relationship. So they go in different directions. So if one goes up and the other one also goes up, this is a positive correlation, okay? So we will continue, we will discuss this a little bit more, especially with the practice that we have, but try to grasp this concept. I don't know at this point if you understand it or if you would like to ask something.
May I ask something?
Yeah, of course.
So how can we then describe the relationship between esteem and SRG if we have the result 0.23? What do we say now then? This is a weak relationship, which means what to the reader or to a philosopher? I mean, how to somehow give meaning to this weak result? Thank you.
Yeah, definitely, Sasha. This is a great question. And yes, this means that self-esteem is weakly related to growth, to a stress-related growth. So this is actually not a good finding. The author is putting it here because they found a statistically significant p-value. This is why it's here, Sasha. And so many authors, they just find a p-value that is below 0.05, and then they are giving you the results, but actually it's not meaning a lot because it's really weak relationship. So here, when you see something like this, you should be skeptical of the main findings of the paper because they don't have the statistical analysis backing the kind of arguments that they are giving you. And one thing that is really important here that I think is actually like really interesting, you can see here like the relationship between cognitive processing and stress-related growth is actually high. It's 0.55. So this is a strong effect. This means that the more you have rumination, avoidance, and hypervigilance when you have diabetes, this means that it is more likely that you will have growth after that, right? So this is a little bit counterintuitive because here you can see the relationship of self-esteem with cognitive processing. So they are thinking that people with more self-esteem should grow more, right? It makes sense. If you are secure of yourself, then you are able to grow more if you are going through this event. However, I am finding here a negative correlation, which is 0.31. 0.31, it is a moderate, like above 0.30, it means like a small relationship. So here I am finding that if I have that, the more self-esteem I have, the less cognitive process that I do. But what is the meaning of that? If having more cognitive processing will lead to more growth, then this is counterintuitive, right? Because I shouldn't have a relationship here with self-esteem because I am explaining more with rumination, avoidance, and hypervigilance. So people that behave like this, it doesn't matter the level of self-esteem, they will actually grow more. So this is the main finding that I am seeing here. So this is important because Personally, I think it's very, very important, even though it seems counterintuitive. If you are worrying about it all the time and then you grow more, it seems counterintuitive. However, it is not, because I remember one researcher that was looking into self-control and the mechanisms behind self-control. Why some people it is able to control themselves and then achieve the things they want to achieve, and some other people are not able to do it. And their finding was that it was not about the personal characteristic of the person. It was not about if they wanted to behave in a certain way in order to actually control themselves. But the key they find, and I think is key here, it was about awareness. How much you realize something that needs your attention is happening, and then you activate your coping mechanisms. And I think it's the same that can be happening here. So people that is ruminating, like hypervigilant, they are aware of their environment, and this is why they are growing more. Right? So this is what I conclude about this. But the most important thing, Sasha, is that like when you are looking at relationships that are below 0.30, you have to be skeptical, even though they are statistically significant. Okay? So it's very interesting. It's very interesting to look at this relationship, and you can have your own theory, and then you can build a research question, and then you can test it. This is research. Okay, I think I have Matthias. Matthias, go ahead.
Yeah. Allow me one other question. What is the name of that data, of that numbers? 0.23, 0.55, 0.34, 0.49. Are that the p-values we spoken former? No.
No, these are the parameter estimates.
The name is only parameters estimate.
Yeah, specifically we have different parameter estimates. Specifically, this is the effect size, and the effect size can be measured with numbers like R, like Pearson's R, like Cohen's T. Okay, so in this case specifically, we have Pearson's R in this model. So these, Matthias, are actually the effect sizes. How strong is the relationship? This is the good data. This is the one you should take a look. So they are here, Matthias, because they are all, the p-value, it is below 0.05. This is why they are on the screen. This is why they put it there. If they hadn't got the 0.05, then they wouldn't put it there, because like it is not statistically significant, and that is the p-value. And we will see that in the paper at the end of the class. Do I have another question? Is it clear so far? Okay, so let's continue. Okay, so let's wrap it up. Inferential statistics. So we start with a research question. We take our sample. We select the model that we have to use, or we build our model, like in the case of, we just saw structural equation modeling. There we are building the model. And then we feed the model to our data. And when we feed the model to our data, we get parameter estimations, like the numbers we were just discussing, 0.31, 0.45, right? And then I run the null hypothesis significant test, and then I get a p-value. And my p-value, as we all know in psychology, should be below 0.05. So this is what I have to look into when I am fitting my model. Also, looking into the statistical assumptions. Remember from the previous session, I told you that in order to use these statistical models, our sample must meet specific characteristics, like, for example, the normality, right? Linearity is another one. For example, homoscedasticity is another one. So we have to meet these assumptions in order to use the statistical test. If one author is not telling you if the sample distribution was normal, you have to be a little bit skeptical of the paper, because they have to test for these assumptions and they have to let you know what happened. And if they were violating some of these assumptions, they should change the statistical model. So all of this should be in the paper, okay? And this should make you trust the paper more. For example, in the paper that we just reviewed for this class, they don't discuss the normalities, the distribution, they don't discuss the assumption, which is sad, right? Okay, so we already know how to use inferential statistics, and we already know that we have different statistical models, okay? I have here 4 examples for you. For example, linear regression is one, t-test is another, ANOVA is another one, and structural equation modeling is another one used by this paper. Now, how do you know when to use one model or the other? This will depend on the kind of research question that you are doing. For example, if you want to find out if religiosity predicts higher levels of post-traumatic growth in individuals, then you apply a linear regression, because you have 2 variables that you are measuring continuously. You don't have groups, so you use linear regression. But what about if you had groups? What about your question being, do individuals who regularly engage in religious practices demonstrate greater personal growth after adversity than those who don't? So in this case, your sample will be different. You will have individuals who are non-religious and individuals that are religious. Because you have 2 groups, then you cannot use a linear regression. Then you have to use a t-test, okay? This is how the statisticians make the difference between which models you should use. So t-test is looking at the difference in the means between 2 groups, only 2 groups. What if you had more groups? For example, let's say you are testing religiousness in different levels. For example, low religiousness, moderate religiousness, and high levels of religiousness. If you have 3 groups, then you cannot use t-test anymore, because it's up to 2 groups. If you have more than 2 groups, then you have to use an ANOVA. So ANOVA is looking at the same thing that the t-test, but between multiple groups. So I am just telling you this for you to know why we use different statistical models depending on the research question that we have, okay? The main thing that you have to take away is that you are testing different null hypotheses in each question. For example, the null hypothesis you are testing in linear regression is that the relationship between religiosity and resilience is 0. There is no relationship. This is a null hypothesis. There are no relationship. This is the one you are testing here. But if you are using groups, for example, in a t-test, your null hypothesis is that you don't have any difference between the means of both groups. If you are using ANOVA, which is more than 2 groups, then the null hypothesis is that the groups means is equal. So you don't have any difference in any of the groups. So you are testing all the time the null hypothesis, okay? So now we are going into the importance of the null hypothesis, how we test it, and what does it mean. But before going there, let me check what time is it. It's 5:50. I don't know why I got some change in in my computer this week, and I think something changed with Zoom and the account that I have from Hochschule. And now my meeting can only last 40 minutes. So I don't know why. It's supposed to be a premium account, but now it is just telling me that it will be off in 2 minutes. So
yeah, I can tell you, the Hochschule has switched from Zoom to Microsoft Teams officially.
Okay.
And I have insisted that my account will not be affected by this. So I still have a Zoom account, the Hochschule. But you should tell the Chancellor that since our project is running, you need this account.
Okay.
And he will pay for it again. Otherwise, you are now on a non-paid account.
I see.
Because otherwise, we would have to switch to Microsoft Teams, which doesn't make sense at that stage of the project. So he should pay for 1 more year for your account. You have to tell.
Yeah, definitely. I will take care of that next week. And for today, in order to close up everything, I will end the meeting and let's please reconnect. I hope there is no.
Okay, we reconnect right.
Yeah. See you soon. It is very, very important if we want to be certain of our prediction. It is very important that we run a null hypothesis significance test. So as we already discussed in the beginning, we want to rule out random variation or sampling error as a plausible explanation of our result, okay? So the null hypothesis significance test explores the probability of getting a result in the population as the one we got in our sample if the null hypothesis is true, right? Which means that there is no effect, as we already discussed. Okay, so we are trying to gather evidence against the null hypothesis. We want to reject it. We want to reject it because if we reject it, then the relationship that we are hypothesizing then exists, right? So we want to gather evidence. But as I already told you, just having the p-value, which is the quantification of the null hypothesis significant test, it is not the whole picture. We need parameter estimates, as we already saw. Okay, so here this is a more detailed definition of the null hypothesis. So we are trying to get the probability of P when given the data, assuming that the null hypothesis is true. So this is the calculation that we are doing with your data. So once again, it's just the probability of obtaining test results at least as extreme as the results that we are observing under the assumption the null hypothesis is true, the likelihood. This is the true definition of null hypothesis significant testing. So the result of this test is the level of significance, or the p-value, which is determined by an alpha level that I establish. So I can say my alpha level is 0.10, 0.8, 0.05, 0.01. So it is a bit arbitrary. So it is just a convention that we have, for example, in psychology, being below 0.05 is good enough. In the hard sciences, sometimes they use below 0.01 in order to be statistically significant. This is just a social convention. So for psychology, it's 0.05, as you already know. So here I have an example of how we are calculating this curve with the test of the null hypothesis, and then we establish a critical value, which is the alpha, as I already told you, can be 0.10, 0.05. And then if I find my extreme value below, like beyond the critical value, then I have to reject the null hypothesis. So this is how it works. And this is how the calculation is being done. So we are using our same data, the same mean, the same standard deviation, how the variance, and we are running this test of the null hypothesis in order to see the result we are getting, the mean, how likely it is that we are getting it just because of chance or just because of error, okay? This is how it works. Now, the p-value only represents how common it is a result like ours if the null hypothesis is true, right? So if this value will tell us if we fail to reject the null hypothesis. However, it won't tell you if we accept our hypothesis. It will just tell us that we failed to reject the null. So we have some evidence for my hypothesis, but it is not corroborate right now. I need to look in the estimator parameters in order to say that. Is this information clear regarding the p-value? Yep. Okay. So obviously, we have some limitations when we are using p-values in psychological science. P-values are often misused. Many researchers, as soon as they got a p-value below 0.05, they are giving you the result I just discussed with Sasha, even though the result is not strong enough. And this is why they are being misused. And this is why you should look into the effect size that they are giving you. You should look into the numbers. In this case, Matthias, into the 0.31, 0.55, 0.45. And this is the level of the strength of the relationship. So how big is your effect? And this is why you should care about these parameter estimates. These parameters estimates, we have different kinds. We have effect sizes, we have confidence intervals, we have standard errors. It can be very complex. However, the important thing is that you master the main ones, like for example, with the correlations, like, you know, if it's above 0.30, then means something, right? If it's above 0.70, then it means a lot. It's really strong finding. All right. This is the kind of things that you should know at this point. And I have for you here, with these statistical models that I already discussed with you, like a linear regression, if I want to predict like the relationship of one variable in another one, a linear regression, this statistical model will give me some parameter estimates. It will give me the betas, it will give me the R-square, and it will also give me the p-value. So all of this will give you the p-value, as you can see here. So p-value is only to know the likelihood of just getting this result out of a random error. But how strong is your effect? It has to do with this. It has to do with this, it has to do with this, and it has to do with this. So if you are looking into a paper that are using linear regression, like you have to care about the R-square, for example, which is the variance explained. If you're looking into the t-test, you have to care about the effect size, which is given to you in a standardized value called Cohen's t, or in an ANOVA, eta square. So these are the values that you should care about. I understand it can be too much to learn them, and we have many different models, but you can use the trick of just reading how they are writing the result. If they are telling you with words how strong is the relationship, then you have, if they are saying we have a strong relationship because of the R square, then you already know. But most of the authors, they don't even tell you like the size of the effect, because they know they don't have an effect, which is the case of the paper that we read for this class. So this is how you can identify the effect size, even though if you don't know how to interpret betas, Cohen's d, or eta square, you can see in the way they are writing, you can already know. For example, I put you here. If you want to interpret betas, so a small effect is around 0.02, medium effect around 0.13, large effect around 0.26, right? This is for R square, just for that. So Cohen's d has a different numbers, eta square have different numbers, and Pearson's R have different numbers. So you can also like have a small annotation with these values, and then you will always know, right? So you can do it both ways. Okay, Godehard, do you have a question?
So did I understand you correctly that in many papers, they give us the low p-value, so telling us the correlation is not just chance, there is something there, but they don't tell us that the correlation is very weak.
Exactly.
So they're hiding, we have found something which is statistically significant, it's not just chance.
Yeah, but it means nothing.
But,
yeah.
but it's just a very, very weak non-chance relationship.
Exactly.
And they hide that the non-chance relationship is very weak. And so it's in another way, again, not significant.
Yeah, exactly.
Okay.
Exactly. This is the main takeaway from this class, Godehard. Thank you. Exactly. And actually the example, the paper that we read for this class, they actually do this, and we will see it in the next screen. It's so funny how they do this, because like it's really obvious, but obviously a lot of people that read this paper, they only go to the abstract and then the conclusions. So they say they ran this fancy statistical analysis, they must know and they must be right, and then we believe the results, when it's not the case. And this is why we are using this course to educate you better and to know better about these things. Yeah. So basically, here, for example, we have correlation, which is one statistical model. So the correlation is really simple model. So we are looking into the relationship of two variables. So you have two directions. It is not one variable predicting the other one, because in this case will be linear regression. It is just how, like, are they related? And how strong is the relationship, and in which direction is going the relationship. This is what a correlation will tell you, right? So the parameter estimates that this statistical model will give you is the R and is the p-value, right? The two. Okay, so here I have for you this chart telling you like there is no relationship at all when it's 0, and when you have from 0.01 to 0.21, it is actually a weak positive correlation. Above 0.30 and below 0.70 is a moderate relationship, and above 0.70 is a strong relationship. So these numbers, you have to master it, like learn it today. So below 0.30, really weak. From 0.30 to 0.70, moderate. And above 0.70, great, really strong effect. Okay? So this is regarding correlation. Now, let's go to our paper for today. This is the paper that we were reading, stress-related growth among diabetic outpatients, the role of social support, self-esteem, and cognitive processing. As I already showed you, they were using structural equation modeling in order to test a specific model explaining this kind of relationship. They concluded that the model they were testing is good and it has a good fit of the data. And the part that I want to analyze with you today is the correlations they are giving you, okay? Which is the topic of today. So here you can see, I ask you to focus on this table, table 2, where they are giving you the results of correlation between the variables and the descriptive statistics. For descriptive statistics, they are giving you the mean, they are giving you the standard deviation, and they are giving you the range. Now, the next thing you have to know in order to interpret this table. Can you see here 2 asterisks? Mean that the correlation is significant at the 0.01 level. This is the p-value. When you see 2 asterisks in the numbers, then you are seeing that a p-value is below 0.01, which is great because it's really, really, really small. This is the thing we want, right? And if you see 1 asterisk, like for example, let me find one asterisk. No, only 2 asterisks, right? Ah, here.
Yes.
1 asterisk. So this relationship, this correlation, the p-value was 0.05, right? So this is the second thing you need to take care with this table. Now, let's take a look at the correlations. I highlighted here for you. Can you see this relationship? 0.75. What do you think of that? Is it strong?
Yes.
Yes, very strong. Very strong. What about this one? 0.11. Weak, really weak, almost null, right? Okay, so I highlighted.
Is that minus 0.11 or?
Yeah, minus means, Sasha, that the correlation is negative. That is, that one variable goes up and the other one goes down. This is why it's negative.
Thank you.
Okay, okay. So great findings, 0.75, 0.39, 0.42. Sounds great, sounds great, sounds great. Okay, however, I have the relationships here, and this variable is self-esteem related with family support. So, and here I have family support related with friend support. And then I have family support and its relationship with other kind of support. So all of these high correlations are just the same variable. So in this case, this strong relationship is that if you have family support, it is likely that you have friend support and you have other kind of support. And these are the ones with the strong correlations. And the other ones here, 75, 39, are the correlation within like cognitive processing. This is cognitive processing. Rumination is highly correlated with hypervigilance, and hypervigilance is highly correlated with avoidance. So this is why they are highly related, because they are actually part of the same scale. So the key correlation that you should care about are the ones related with the main variable, stress-related growth. So what variables are strongly related with the stress-related growth? Can you see here? All of them are really weak. 0.29, 0.23, 0.24, 0.26, 0.24, 0.28, all of them. And this is the main variable, right? So let's take a look of what the authors actually wrote. The sample, like here, for example, as can be seen from table 2, stress-related growth scores were significantly correlated with dimensions of social support. Yes, they were statistically significant related. I can see it here. However, the relationship is not either moderate, not strong. So this is what I meant, Godehard. They are telling you they are significantly correlated, but I don't have a good effect, right? It's really a weak effect. And this is why they are not telling you anything about the size of the effect, because there is none. This is the key part. And they say the same for the other variable, for cognitive processing, and they say they are significantly correlated. Yes, it is significantly correlated. However, very weakly, 0.27, 0.31, and 0.28, all below. No, the only one above 0.30 is actually, this is really good. I actually like this finding. As you can see here, I have above 0.30 and number 8, I go here, number 8, avoidance. So the more cognitive processing you do and the more you avoid to think about your diabetes, the more you grow. This is very interesting because it is actually making an argument against the model, because they say that going through this disease will make you grow, but it's actually just avoiding thinking about it is the strongest correlation among them. So this is actually speaking against the main hypothesis. And this is the kind of things that you can already distinguish just by knowing the strength of the relationship and understanding all of this. For example, here, these values, you don't see any asterisk. This means it is not statistically significant. Okay, Matthias, what do you think about it? Because you have asked me before many times about how to read these tables. Is it clear?
I think he has left.
Oh, okay. I hope it was clear now.
May I ask a question?
Yeah, go ahead.
Like just a short one, like you said, 0.31 avoidance is like very interesting, but then we have rumination 0.28. That's like difference only 0.03 difference between 6 and 8. And then, I mean, with such a small difference between rumination and avoidance, can I just like neglect rumination and say, okay, that's below the threshold of 0.3, and we need to look at avoidance that is 0.31. I mean, there is, yeah.
So you are looking into 0.27, this one here?
No. I'm looking at number 6, 0.28 rumination.
Here. Okay, rumination.
And growth. And then I'm comparing it to number 8, avoidance, that is 0.31. And you said like this is really a good result, interesting result, but then the difference between 6 and 8 between rumination and avoidance is only 0.03.
Yeah,
so
exactly. Yeah, you have a great point, Sasha. You have a great point. And as I showed you before with the common cutoff, so it is a consensus between researchers in psychology that values below 0.21 are weak and above that are moderate. But this is a social convention. The question that you are asking is valid. Like, come on, it's just 0.3 of difference. And this is how science, in this case, psychology, can be arbitrary. So in this case, you are right. It's very similar. It's very similar. The strength is very similar. The difference is not big. So you have some more evidence about what is happening in your phenomena of inquiry. However, you don't have a strong enough information to make any claim. So
okay,
in this case, I will go with you and say, come on, the difference is too low. Basically, I will say that we need more studies in order to know more. And we know we need a specific hypothesis looking into a specific relationship. For example, here I have a lot of noise with self-esteem because self-esteem is negatively correlated with cognitive processing. And they were saying having high self-esteem will lead you to grow in this traumatic disease. However, we are seeing that the more variance that is explained by cognitive processing, which is the opposite relationship with self-esteem. So in this case, this model is faulty, using self-esteem in this way. And this is why we cannot trust the values. So all of this information is you like getting clues of how things are actually going wrong, and you cannot trust the final arguments of the paper, Sasha. Exactly.
Thank you.
Okay, guys, because I think Sarah is not here also. Oh, see, Sarah is here. Okay, so this is inferential statistics, and these are statistical models, and I know some concepts can be hard to grasp. Basically, the main thing to take away is, as Godehard already said, like you need to look into different things in order to believe the claim the author is giving you in the abstract or in the discussion. So be careful. Now you know more how to look into the results and learn this about the strength of the relationship. Like this correlation thing, being positive, negative, will help you a lot when you are interpreting papers in psychology. So this was it for today, inferential statistics. The next session with me, we will have a little bit more of inferential statistics because sample size, the size of your sample influence a lot the p-values. This is another trick. A lot of people is using big samples and they are getting p-values that are below the threshold, but then no effects. So this is one more thing that you have to be careful when you are reading the papers. But we will discuss this in the next session.